Thanks for tuning into this Revision Zone Maths video. In this video, we're going to be looking at composite functions. So let's start with a definition. What is a composite function? A composite function is basically a function which is built from two or more functions, right? So let's write that down. Composite functions. A function which combines two or more functions to produce a new function is a composite function. So to get a better sense of what I mean, let's actually look at a few examples. So suppose we have this case. We have f of x is actually, say, 2x, that's a function. And suppose we have another function, which is, say, g of x, and that's, say, x plus 1. That's another function. So we have two functions. What we could actually do is we could say, let us take x as our input. Say we first apply the function f to get 2x. But then once we've got that, we actually apply the function g. Okay, so what does g do? G takes in a number and it adds 1 to that number, right? So in this case, g is going to take in 2x and we're going to add 1 to it. So we're going to end up with 2x plus 1. So now this overall thing that we've actually got here, so the function going from here to here, this thing here can be defined as a composite function. And of course, I should have said that actually, given that this is our input, then this thing here is going to be our final output. Okay, so here we've actually taken two functions and we've sort of combined them in some way. We've applied the first one, then the second one to be able to get this overall function here, right? And the way we would write this down is we would say we start with an input, which is x. We first apply f to it, and then we apply g to the whole thing. So this is the way we write down composite functions. And in fact, more conventionally, they can be written like this. Okay, so we're writing f and g next to one another. And in writing it this way, we know that the x is going to see the f first, and then it's going to see the g, right? So that's what composite functions are. Let's consider another example. So we might again start with an input x. But in this case, say we apply the function g first, okay? So what does g do? G just adds 1, so I'm just going to get x plus 1. And then from here, say we go on and actually apply f, right? And now we need to think about what f does. Well, whatever the input is, f just doubles it, okay? So in this case, my input is x plus 1. So when I actually apply f to it, I'm going to get two lots of x plus 1. So perhaps I'll write it down like this. And of course, we can simplify that to say 2x plus 2. So again, we have this thing here, the overall thing actually being our composite function. Okay, and I should also add that, of course, here x was our input and 2x plus 2 was our final output. So you see, the function in this case, the composite function, is where we started with x, we applied g to it, and then we applied f to the whole thing, right? And of course, more conventionally, you would write this as like this, where now you see the input x is seeing the g first because the g acts on x first. And then it sees the f afterwards because the f acts on the entire thing afterwards. Okay, so this is another example of a composite function. So let me maybe say that here. So we could say e.g. So we've now seen two examples. Now, you might actually notice that actually what we did in the first example compared to what we did in the second example, we get slightly different answers out, right? So in other words, this thing here is actually 2x plus 1, but this thing at the bottom here is actually 2x plus 2. So what we've actually shown is it really matters which way around you sort of compose functions, okay? So f of g is not the same thing as g of f, right? And there are lots of other properties of composite functions that are going to be generally true. So perhaps it's worth making a few remarks to sort of describe these properties. So let me make a bit of room and let me go and do that. So remarks. these are the things you need to know when dealing with composite functions. So let me just say need to know. Okay, the first thing is when you actually write this down, as I've already sort of said, the X is going to actually see the G first and it's going to see the F afterwards. Okay, so X is going to see the G first, so you're going to have G of X first and then you're going to have F, right? In other words, when we actually write functions down, we read from the inside out. So let me maybe say that here. So read from inside to outside. I say this because a lot of people make this sort of mistake quite often, which is they presume that just because in the English language we read from left to right, that they will just read this from left to right. But that's not how these sort of things are defined, right? So just be mindful of that. The second thing I would say is, as we've actually already seen, that order matters. So f of g of some input x is not the same thing as g of f of some input x, right? So I would say order matters. So just be very careful about that when you're actually doing these things, you're very conscious of which way around you're doing them. The third thing I would say that it's actually quite important to understand that when someone writes down f of g of x, they do not mean that it's f of x multiplied by g of x, right? So when we actually put f and g next to one another with nothing in the middle, that does not mean that f and g are being multiplied, right? So this is not true. In fact, just to avoid this confusion, sometimes book use like a circle, right? So they would write down a circle in between f and g, and they would do that. So what this would mean is basically the exact same thing as this thing here, right? So so you may see this in other contexts as well. And the fourth point I actually wanted to make is as follows, which is we've got to be very careful how we actually combine functions. So in particular, if you've got, say, some domain, and let me say this is the domain of some function f, and then you've got the function f acting on the domain to give you some sort of range, right? Range of f. Then if you've got another function, say g, and obviously these are the domains and the ranges of g respectively, then in fact, to be able to define the function f of g, right, or even g of f, what we need to have is we need to have compatibility between the sort of range and the domain, right? So what do I mean? I mean, say you've got f of g. So the input is going to see the g first, and then it's going to see the f afterwards. So it's going to start here somewhere. It's going to see the g, and it's going to come here, and then it's going to want to see the f. But the point is that only really makes sense if the range of g actually coincides in part with the domain of f. Okay, so in other words, I can say we can have something like that, and that thing there could be the range of g. Okay, so f of g is defined. F of g is defined only when the range of g is contained in the domain of f, contained even partly in the domain of f. And similarly, let's look at the other case where we've got g of f. Here, the input's going to see f first, right? So we're going to start with somewhere here, and it's going to see f first, and it's going to end up somewhere here. And then it's going to actually see the g. That means this function here is going to be acting on the thing that comes out here, right? But that can only really happen if the thing that actually comes out here happens to also lie in here in some sense. Let me use a different color maybe, and I can say here, and let's mark that, and let's say this is range of f. Okay, so I can again say gf is defined only when range of f is contained partly in the domain of g. Okay, so I hope that's clear. I will actually do another schematic or two just to be able to really express this idea much more concisely. So this schematic is perhaps a much better way of explaining what I was trying to say, which is you have to have compatibility between the domain and the range of the things that you're actually working with, right? So suppose we actually want to define the function f of g, okay? And we see that we're going to start with x first, that's the input, and it's going to see my g first, so that's what's happening here, and it's going to give me something which is g of x, but that's going to have to live inside the range of g, okay? And then for me to be able to apply f at all, the thing that I've actually already got must be inside the domain of f, because if it's not in the domain of f, the function f is not defined on it, right? But if it is inside the domain of f, then we can apply the function f to it, and we can actually end up getting f of g of x, right? So the compatibility is actually quite significant, and indeed, if this compatibility exists, then we say we can actually go from x to f of g of x straight away, and so the function f of g actually exists, okay? So in fact, let me make that point on the side here, which is if the domain of f and the range of g are compatible, then f of g is well defined, right? But this need not always be the case. So indeed, let's quickly consider an example of a case where, f of g is not going to be defined, right? So let me define my g of x such that it is minus x squared, where x can be any real number, but x cannot actually be 0. So the input is not allowed to be 0. And let me take my f of x to actually be the square root of x, right? And of course, the domain in this case is x can be any real number, provided that x actually is positive. Of course, I could also say bigger than or equal to 0, right? That shouldn't really make that much of a difference. But let's now think about this. Let's think about what's going to happen. So we're going to start off with x, and then we're going to apply g, and we're going to get negative x squared, and then we're going to want to apply f. And here's the problem. The problem is this thing here is always going to be negative. And the function f is only really defined on a positive input, which means that input into the function f has no chance of giving anything as output which is sensible, right? So in fact, what we actually come here and say is not defined. And this is a concrete example of a case where the output of g, right, which is going to be negative sort of numbers, is not compatible with the input of f, which has to be positive numbers, okay? Anyway, so let's now go and look at lots of examples to get a better handle on composite functions. Example 1, we're basically given two functions and we're simply asked to compute two composite functions. Let's just jump in and do this. So solution, I want to compute, say, f of g of x first. And of course, as we know, we've got to read this from the inside to the outside. So what's going to happen is I'm going to have g acting on x first, and then f is going to act on the entire thing. So now we know what g of x is. G of x is just log x, right? The question tells us that it's the natural log of x. So we now want to evaluate f of the natural log of x. But we know what the function f does. F takes in something and it just cubes it, okay? So now it's taking in log x and we're just going to cube that. So I'm just going to have my natural log function, and in the end, I'm going to cube everything. So this thing here is now my final answer. This is my composite function. Let's think quickly about the domain and range of this sort of thing. So let's think about g first. So we've got g acting on x to give me log x, and then we've got f acting on that to give me log x cubed. Well, you can only really take the log of numbers which are not negative, okay? So here, the input is actually the real numbers which are actually bigger than 0. And then the output here, obviously, is going to be every single real number, because if we look at quickly the graph of log x, it does something like that, okay? So we know that actually it's allowed to only take in sort of negative x values, and then it can give out every single possible y value. So with that, we can now think about what f does. Well, f just takes something in and it just cubes it, right? But it's taking in every possible real number, and indeed it is possible to cube every possible real number. So this is completely well defined, and then the thing we're going to have come out is every possible real number, right? So the domain of, let me write it here, the domain of f of g is actually all the real numbers which are bigger than 0, and the range of f of g is actually every single possible real number. Okay, so that's the first one. Let's now think about the second one. Let me make a bit of room. So the second one we want to think about is actually g of f of x. Okay, so perhaps I'll draw a line here separating this out from the work we've done at the top. So here we're again going to read this from the inside to the outside. So here we're going to have f acting on the x first, and then the g is going to act on the f. But now we know what our f of x is. F of x is just x cubed. So in fact, we're going to have g of x cubed. And this is where things get a bit more interesting, because our g function is basically the log function, and g tells us that whatever the input is, you take the log of it. And in this case, the input happens to be x cubed, so we actually go and take the log of the x cubed. So we've again managed to figure out our composite function, and no surprises that swapping the order from before, we actually have a very different function in this case compared to before. So let's think again about the domain and the range. So we start with x, but then we apply f first, and we end up with x cubed, and then we apply g, and we actually end up with the log of x cubed. So let's think about this. So indeed, we can cube any real number, right, to be able to get a real number. So we know that the domain of f is just real numbers, and the range of f is also real numbers, okay? But then this is where we start to run into some problems here, because g will not accept every single possible real number, right? As I sort of already showed this earlier, that if I actually have a graph of log function, then it's only really going to accept, right? Let me call the inputs u. So it's only really going to accept positive values for u. So we need to be slightly careful when we talk about the inputs going into G. So what we're going to do is we're going to say we want to actually, let me do it in a different color, we want to actually restrict this. So restrict to being real numbers, which are actually necessarily positive. But to be able to do that, we've actually got to restrict this. So we say restrict to real numbers actually being positive. And once we've done that, now G is a lot more happier. It can take in these inputs. And of course, the outputs we're going to get are going to be real numbers. So let me perhaps tidy this up on the right-hand side and then write what the domain and the range are going to be in this case. Okay, so the domain of G of f is going to be all the real numbers, which are actually strictly bigger than 0. And the range of G of f is actually going to be all the possible real numbers. Okay, so I hope you found this example useful. Let's go take a look at the next example. This example is very much like example 1, but now it's worded somewhat differently. As we can see, it's using the sort of composition symbol as opposed to the notation we've seen so far. But really, this is very much like the example we've seen in terms of the content of the actual mathematics here, right? So we're given two functions, and we're given the domains for those functions, and then we're asked to work out two separate composite functions, and then we also have to work out their domains and ranges. Okay, so let's jump in. I'm going to do this slightly differently, just so we see how we can reason in different ways here. So we, of course, start with f compose g of x. And we know that this is nothing other than f of g of x, right? And then in the past, we actually substituted for g at this stage by going to the description of g. But now I'm actually going to use the definition of f, okay? So f tells me that whatever the input is, I square it, and then I take away 5 copies of my input, right? Well, in this case, my input happens to be g. So what I can say, I actually square my input, which is g, and then I take away 5 copies of my input. So this is what we end up with. And now at this stage, we can just substitute in for g, the algebraic description for g. So this is essentially our composite function, but perhaps it will be nicer to write this in a simplified form. So we can factorize the 2x plus 3 out, because there are 2 copies of 2x plus 3, and we end up with this. And now we can actually go ahead and simplify the term on the inside. So the 3 minus 5 is just going to give me minus 2. So I actually end up with 2x plus 3 and 2x minus 2. So this is basically our composite function. And the only thing that's now left is to figure out the domain and the range. So last time we did this, we said, that we actually have some x, and then sort of g acts on the x to give us g of x. And then the f acts on the g of x to give us the f of g of x. And we went away and thought that, well, actually, in this case, we're going to have for the g is going to have real numbers as input. So I'm just going to have real numbers here. But I know that for straight lines, every real number can be an input, and also every real number can be an output, right? So I know that this is going to be just reals. But then I can now say, for f here, I can just think about this, and I know that this domain here is compatible with the domain of f, because indeed we've got real numbers in both cases. And so what I can say is the range here actually is going to be nothing other than the range for just f by itself. Okay, so let's figure out the range for f by itself. So let me maybe do that here. So range of f of x, and let's say question mark. Well, we can figure that out because we've got f of x is x squared take away 5x, and we know that we can just basically complete the square on this. So we can say x take away 5 over 2 all squared take away 5 over 2 all squared, right? And that's nothing other than just something like x take away 5 over 2 all squared take away 25 over 4. Okay, and we know that basically when we put a quadratic in this form, we know that we can get the coordinate of the vertex. So we can say the vertex is actually at 5 over 2 and negative 25 over 4. So we've managed to get the graph of f of x, and we actually see that the range here is necessarily going to be everything here. So everything on the y-axis, which is more than negative 25 over 4. So I can now come back here to my description, and I can say the range here has to be all the real numbers, which are actually strictly bigger than or equal to negative 25 over 4. So we've actually managed to figure out the range for f of g of x, and also the domain for f of g of x, because effectively this thing here is f of g of x, right? So I can say the domain is the real numbers, and the range is actually real numbers which are bigger than or equals to minus 25 over 4. So the interesting thing here is we've actually used the description of f in itself to work out the range in this case, right? Whereas last time we sort of reasoned somewhat differently. The other thing that's perhaps worth saying is actually we could also have done this a very different way, which is we could have just gone to f of g, and we know that what the domain for f of g is, and then we could have just said, let's just work out the range directly from f of g as opposed to worrying about f, right? So let's maybe see that as a remark here. So we know that f of g is basically this thing here, which is 2x plus 3, and it's 2x minus 2. So let's sort of expand this out. So I'm going to get 4x squared and then I'm going to get minus 4x plus 6x minus 6, which of course we can simplify to say it's going to be 4x squared plus 2x minus 6, which I want to do the same sort of thing now because I know that the vertex is going to be the key, right? I want to work out the vertex of this quadratic here, so we need to complete the square on that. Of course, we could go away and use differentiation and other things, but let's just complete the square to keep life sort of straightforward. I don't mean to write that. I mean to write this. Good. So we've got that. And then now we want to complete the square. So it's going to be 4, and it's going to be x plus a quarter squared, take away a quarter squared, and then it's take away 6. And now we can say 4 x plus a quarter squared, and of course this negative of a quarter squared is going to give me 1 over 16, and I'm going to times that by 4 to give me 4 times by 1 over 16 to give me 1 over 4. So I'm just going to end up with negative 1 over 4 negative 6, right? But perhaps it's nicer to be able to combine this in one step. So negative of 4 negative 6 is just negative 6 and a quarter. So I'll just write that down. Negative 6 and a quarter. So here we have it. Right, so we now have our vertex in this case, right? And the interesting thing is negative 6 and a quarter is actually the exact same thing as negative 25 over 4, right? So if I, for example, convert this maybe here, so negative 6 and a quarter is exactly the same as negative 25 over 4. So we know that the range in this case is actually, if I come back and say it's still going to be bigger than equals to this, which is of course just that, and the domain in this case is actually going to be that. So we've been able to check our answer a different way. I hope that's useful. Let me make some more room and then we'll try the second part of this and sort of do that rather quickly. So moving on to part 2 of this example, we now want to work out g composed with f, but that's obviously the same thing as g of f of x, which we can write as follows. And as before, I don't necessarily want to substitute in for f here. Instead, I want to go to the definition of g, and we know that g takes in an input, it doubles the input, and then it adds 3. Our input just happens to be f of x, but g is going to do the exact same thing it does. It doubles the input, and then it adds 3. And at this stage, I can actually go to a description of f of x directly, right? So f of x is going to be x squared take away 5x, and then obviously the plus 3 is still there. Okay, so now we're basically done because this is our composite function. It's 2x squared minus 10x plus 3, and we know that our domain for the composite function, we're going to start with x, and we're going to basically end up with f of x first and then g of x acting on that, but we're going to go through that via going through f of x first. So of course that means that f is going to act on x first, and then g is going to act on that as a result. F has domain real numbers, but of course f is not going to have range real numbers. We worked this out in the sort of previous part of this example. It's going to have real numbers which are going to be bigger than equal to minus 25 over 4. And then g is going to have sort of domain all the real numbers. So that's fine because that's part of all the real numbers. But then we're going to have to figure out what the range is going to be in this case. So given that our graph of g is going to look something like this. So we're going to have, this is g of x. We want to figure out for x being minus 25 over 4, what the corresponding y value is going to be, okay? So there's going to be some corresponding y value. So this is a terrible sketch. There's going to be some corresponding y value, and we want to figure out what that y value is, because once we know that, then we know that actually the range is going to be everything sort of above that y value on the y-axis, including that y value, of course. So let's figure that out. So what we're going to basically have is we want to figure out g at minus 25 over 4, right? Well, that's exactly the same thing as 2 times by minus 25 over 4 plus 3, which is minus 25 over 2 plus 3, which is minus 25 over 2 plus 6 over 2, which is of course just minus 19 over 2. So we actually know that this point here is minus 19 over 2. So our range is actually going to be all the real numbers which are bigger than or equal to minus 19 over 2. Okay, so we've managed to figure out the range in this case. But of course, you could have also have gone to just this directly, and then you could have worked out the vertex of that. And then from that, you would know what the range is going to be, right? So I think that's a good place to move on to the next example. Example 3 is quite interesting. We again have to work out a composite function, but the interesting thing here is one of our functions is actually a piecewise function, right? Because the modulus function is known to be a piecewise function. So the point is we can actually have composite functions that are composites of piecewise functions, and obviously as a result we're going to get more piecewise functions. So let's see what the solution is going to look like. So we want f of g of x, which of course is nothing other than this thing here. We've now seen this lots of times. So now there are multiple ways forward here. I can either substitute in that into here, or I can just say, let me apply the definition of f using that, right? So let me just do the latter. Let me apply the definition of f. So I know from this definition here that if I actually apply it here, I'm just going to get 9 take away 4 times by g of x, and then we want the modulus of the whole thing. So basically I've done nothing other than let g of x play the part that x actually plays in that definition there, okay? So at this stage, I can now substitute in what the description of g of x is. So I can say 9 take away 4 times by g of x is just 3x take away 2 all over 2. Okay, and then we can maybe tidy this up a little bit more. So we can just say 9 take away, well, the 4 times 2 is going to give me 2. So we end up with this. And then we can expand the bracket to say 9 take away 6x plus 4. And then, of course, the 9 plus 4 is going to give me 13. And I end up with 13 take away 6x. So this is basically our composite function. You might actually want to see it in this form, which is the expanded form, where basically it's going to be this thing here for when that thing there is positive. So it's just going to be 13 minus 6x when 13 minus 6x is actually not negative. And it's going to be negative of 13 minus 6x precisely when 13 minus 6x actually happens to be exactly negative. So this is our piecewise function, okay? We're not asked to worry about the domain and the range in this case, so we really need not do that. But if you actually think about it, this is going to have domain every single possible real number, and it's also going to have range every single possible real number. But this is going to have domain every single possible real number, but the range is going to be everything which is non-negative, okay? Therefore, it's not too hard to figure out that this thing here is going to have domain every single possible real number, but the range is going to be every possible thing that is non-negative, right? So that's pretty much the example done, but let's quickly look at a remark. And the remark might be, what if I actually wanted to calculate the exact same thing using the piecewise definition of the modulus function? So that can be done. So we basically end up with this, where here, and at this stage, what we can say is we can actually go to our description of modulus function. So we can say it's going to be this thing here for when that thing there is positive. So we can just say it's going to be 9 minus 4 times by g of x, precisely when 9 minus 4 times by g of x is actually like this. And it's going to be negative of 9 minus 4 times by g of x, precisely when 9 minus 4 times by g of x is actually negative, okay? So now, if you think about what's happened, well, we had 9 minus 4 times g of x here, right? And we substituted g of x here, and therefore, by the time we get to there, we've actually done nothing. All we've done is we've literally taken this, we've substituted to get this, and then we've just simplified. So in other words, this thing here, because it's exactly the same thing as this thing in the bracket here, and that's all exactly the same as this thing here, I can just come back and say the piecewise description can just be written as 13 minus 6x, and then it's going to be 13 minus 6x bigger than or equal to 0, and it's going to be minus. I've got 13 minus 6x, and the whole thing is 13 minus 6x is strictly less than 0. So we end up with the exact same thing. Let's take a look at the next example. Example 4, we're given an equation that we have to solve, but the equation is described in terms of having a composite function on the left. So let's see what the solution is going to look like. So we've got a solution, and of course we have f composed f of x being equal to x. Well, that's the exact same thing as saying f of x is actually equal to x. So before we actually do anything, we need to figure out what this thing here is, right? So let's do that. Well, f of x, by just looking at the definition of what f of x actually is, whatever the input is, we add 1 to it and we put it in the denominator. Okay, so our input actually happens to be f of x in this case, so we add 1 to f of x, and then we put that in the denominator, and of course there's a 2 in the numerator always. And since we know what f of x is, because we have that there, we can now just put that back in. So we can just say this is the same thing as 2 over x plus 1 all over plus 1. So now it's just really a matter of simplifying this. So what I'm going to do is I'm going to sort of make a common term here. So I'm going to multiply top and bottom by x plus 1. So I end up with that over 2 over x plus 1 plus x plus 1 over x plus 1. And then we can indeed leave the 2 there and just combine the top here like so, and then we can have x plus 1 here, and this is sort of standard algebra. When we know we've got something of the form a over b over c, we know we can sort of flip that to say ac over b. So I'm just going to have 2 times by x plus 1 all over 2 plus x plus 1, and I need not worry about the brackets in the denominator. So now we can switch back color, and we can actually say our equation here actually can be written as follows. It can just be written as 2 times by x plus 1 all over 3 plus x, and we want to solve that to actually be equal to x. This is straightforward, so we just multiply through by the denominator, so we actually end up with this 3 plus x times by x, and then we just sort of expand this out. So we say it's going to be 2x plus 2 is equal to 3x plus x squared, and then we just rearrange to say, actually, I can keep my x squared, but then when this 2 comes to that side, I'm going to get 3x minus 2x. That's going to give me x. And then when this 2 comes to that side, I'm going to get minus 2x, okay? Or minus 2 even, and of course that's equal to 0, and then we can actually go on and sort of factorize this. So we can say x plus 2, and we can say x minus 1 equal to 0, and then that basically tells us that x is either 1 or x is either minus 2. So we actually have 2 solutions here. So there are a couple of remarks. The first remark is, let us just check if this is actually a sensible solution, say. That's an easier number to be dealing with than that for now. So let's see. So we want to figure out what f composed f is at 1. Well, we know what f composed f is. That's the formula for it, which is written in a much more elegant way here. So let's put that in. So I'm going to basically say it's going to be 2 times by 1 plus 1 over 3 plus 1. Okay, and that's the same thing as 2 times by 2 over 4, which is of course 4 over 4, which is nothing other than 1. And indeed, that's exactly what we put in the first place, right? So that balances the equation. And I would say to you to maybe check that for yourself, and you'll see that the equation would still be balanced in that case as well. Okay. The second remark would actually be as follows, which is, notice that f of x is actually not defined for x equals minus 1, right? But f composed f is not defined for x equals -3, okay? And we see that here, because if we put -3 in here, that actually causes problems, okay? So the fact is, if you figure out this function here, f composed f, this is an entirely new function, and it's going to have, in many ways, entirely new properties compared to the function that you actually started with. Of course, there's going to be some relationship from the old one to the new one, and you'd be able to link the properties from the old one to the new one, right? But a priori, there is no reason for you to necessarily expect that the properties are going to be exactly the same, right? So if you are interested, the link in this case would be as follows, that actually, if you figure out f at -3, then that is actually going to give you -1, okay? So in other words, when you've actually got this composite function here, if you were to put -3 in the first part, well, that's completely fine. That's sort of putting -3 in here, and f of x is completely defined for -3. But the problem is, the minute you put -3 into here, then f of -3 actually gives you -1. And we know that f is not defined for an input of -1. So that's really the link. But anyway, let's take a look at the next example. Example 5, we're given two functions and we're asked to basically describe the transformation that will happen if a third function was composed with the first two functions that were actually given. So this is a very interesting example. So let's see what the solution is actually going to look like. So we want to first of all figure out what this function is actually going to be. So this is clearly a composite function just because of the fact that we have an f and g there, but actually this is a triple composite function because e to the x itself is actually a function. Okay, so let's see what this looks like. So I've got f of g of e to the x, but of course we work from the inside to the outside. So I'm going to start with e to the x, and then I'm going to have g act on that, and then I'm going to have f act on the whole thing. So it's going to look like this: e to the x, and g is going to act on that, and then f is going to act on the overall thing. Well, what does g actually do? G just takes away 4. So whatever the input is, g is going to take away 4 from the input, right? My input happens to be e to the x, so we're just going to take away 4. So we're going to get e to the x, take away 4. And now let's think about what f does. Well, whatever the input is, f just triples it, right? So my input happens to be this thing here. F is just going to triple that, so I'm just going to end up with 3 lots of my input. Okay, so this thing here is now my composite function. So we're going to go from y equals e to the x, and that's going to be transformed to y equals e to the, or rather y equals 3 times by e to the x minus 4. Okay, and we now have to basically describe what this thing actually is going to do, right? So in other words, what's going to happen to the graph of e to the x to be able to get the graph of this thing here, okay? So there are lots of ways of doing this, but I would like to do it as follows. So I'm going to say, let me just take my e to the x actually to be h of x. And what's happening here? My h of x is basically going to 3 copies of h of x, and then I'm taking away 4. Okay, so this is fairly straightforward. We know how to describe this sort of thing. We obviously work from the inside, and what's happening is we're taking away 4 on the outside of that function, which means we're going to start off with a translation. So it's going to be translation of 4 downwards on the y-axis, obviously, and then it's going to be a stretch by a scale factor 3 on the y-axis because the 3 is on the outside of the overall thing, and this is going to happen afterwards because this is outside the bracket. We work from inside the bracket to outside the bracket. So then we're going to have stretch by scale factor 3 along y-axis. That's basically it, okay? So I should perhaps say then here because order is really, really important. Right, so that's that question done. Let's just quickly look at a remark, and the remark might be as follows. Well, another way of being able to write this would be something like this. So I could have said my y equals 3e to the x minus 4 with these things in brackets, of course. I could have said this is the same thing as 3 times by e to the x minus 12. Okay, and now if I actually look at the exact same transformation, I can lay it out slightly differently. I can say now my e to the x is actually going to 3 lots of e to the x minus 12. And if I actually take my h of x to be e to the x again, that's the same thing as I've got 3 copies of h of x, and then I'm taking away 12. Well, if I now think of this, because we're going to work by basically from inside to out, and we're also going to have to respect BIDMAS, I'm going to have to respect that multiplication first. So in this case, what's going to happen is we're actually going to have a stretch. So we're going to have a stretch by scale factor 3 along the y-axis, and then we're going to have a translation. And the translation now is not going to be a shift of 4 downwards. It's now going to be a shift of 12 downwards. Okay. So let's write that down. So perhaps you might want to go away and use some sort of graphing software, or maybe go to Desmos or GeoGebra or something, and just see that actually if you were to sort of graph either that or graph either that and made different choices for h of x, doesn't really matter. You could just take e to the x, but you could equally take other well-defined functions. You will find that both these transformations, both these descriptions are going to give you the exact same thing, right? Provided you do it in the right sort of order. So provided you shift down first, then stretch by 3, or provided you stretch by 3 along the y and then you shift down by 12, you'll get the exact same thing. Anyway, so that's a good place to end the video. So thank you for watching. We hope you found this useful. If you did, please sort of hit the like and subscribe buttons. As always, do let us know in the comment section as to what you would like to see more videos on, and we will see you in the next video.